In the previous lab, we were looking into step 4 to estimate causal effects. The one thing we noticed from the propensity score matching of this work is that classification and regression methods are used in the process of propensity score matching. This leads us to a more data-driven or machine learning-based method where we can rely on the use of machine learning instead of propensity score matching. The causal forest is a machine learning method used for estimating causal effects in observational studies. It's based on the notion of using forest of trees to approximate conditional average treatment effects, which is the average difference in outcome that can be attributed to a specific treatment for a given subset of the population. The causal forest is an extension of the popular random forest algorithm. It introduces the concept of treatment variables and uses them to partition the data into subsets. For each subset, a separate causal effect is estimated. This allows the model to capture heterogeneous treatment effects, meaning that the effect of the treatment can vary across different subpopulations. So mathematically, the causal forest can be described as follows: data representation, objective function, partitioning data, estimating conditional average treatment effects, ensemble of trees, heterogeneous treatment effects. So the constant marginal effect represented the estimated constant marginal effect of a treatment variable on the outcome variable. In the context of causal inference, the marginal effect quantifies the change in the expected value of the outcome variable associated with a 1-unit change in the treatment variable while holding all other variables constant. In simpler terms, it tells you how much the outcome variable is expected to change on average when the treatment variable changes by 1 unit, assuming that all other variables remain the same. For example, if we are studying the effect of a new drug treatment variable on blood pressure outcome variable, the constant marginal effect would tell us how much we expect the blood pressure to change for each additional unit of the drug, regardless of the specific dosage. Now, let's plot histogram of the um, Kate, and Kate is let me check. Kate is conditional average treatment effects. Okay, so let's plot histogram of conditional average treatment effects of treatment variables worry crime and worry weather. DFNZ dot Kate of worry crime dot hist of bins equal 50, comma label equal worry crime, and DFNZ dot Kate worry weather dot hist of bins equal 50, comma label equal worry weather. plt.legend, open and close bracket, plt.show, open and close bracket. So from the histogram, we see that worry crime and worry weather, they show the normal distribution kind of curve, but worry crime is more is on the starts on the left, and the bell chart starts on the left, and then there is worry weather. So the range of the worry crime the range of the worry crime. So let's plot this separately to see the range clearly. Okay, so the worry crime, the range is from about minus 0.6 to about minus 0.2 to about 0. So looks like worry crime. The um, conditional average treatment effects are negative values, and it is normally distributed around about, so we're trying to find the middle value, say minus 0.35. In worry weather, the range is from about minus 0.4 to 0.2. So there are some positive conditional average treatment effect from worry weather. So here, an unit increase in worry crime would increase the perception on personal safety by 30%. %30% is safer. For weather, there is a large variation of how people worry with weather events would cause their perception in safety. Some people hugely worry about it and some not. Okay, so in this lab, we could we perform another pair of treatment and outcome variables choosing from the Bayesian network we did above. So let's define the outcome as experienced mental. Let's define the treatments as worry work and worry mental. Let's look at these three variables in the um, directed acyclic graph. So we have worry work, worry mental, and we have experienced mental. Let's look at these three variables in the acyclic, directed acyclic graph. Okay, so okay, so this is the graph. So the three variables are worry work, worry mental, and experienced mental. Worry work, worry mental is here. Experienced mental is here. So worry mental and experienced mental are connected, and worry work. And worry work is connected to worry mental. Okay, so these three nodes are connected. Okay, so select all numeric variables. Let relevant variables equal df and z dot select underscore data types of include equal array of np dot number dot columns dot to list open and close bracket. Make sure to remove the outcome and treatment variables from relevant variables, assuming, okay, so let relevant variables equal array of var for var in relevant variables if var not in worry work, worry mental, and experienced mental. Define control variables. Let W equal df and z of array of relevant variables. Initialize a robot scalar instance. Scalar equal robot scalar open and close bracket. Fit the scalar on the control variables and transform them. So let W scaled equal scalar dot fit underscore transform of W. Specify models. Let model Y equal random forest regressor open and close bracket. Let model T equal random forest regressor open and close bracket. Define treatment variables one at a time. For treatment variable in treatment variables colon, define T for this treatment variable. Let T equal df nz of double square bracket of treatment variable. So we're forming the data frame of each of the treatment variables. Define the causal forest estimator. Let est equal causal forest dml of model y equal model y, model underscore t equal model t, featureizer equal polynomial features degree equal 1. Fit the model. est.fit of y dot revel open and close bracket dot t comma x equal w scaled comma w equal w scaled. Calculate the constant marginal effect for this treatment variable. Let const marginal effect equal est dot const underscore marginal underscore effect of x equal w scaled dot revel open and close bracket df nz of f apostrophe kate underscore, so that will be the string kate underscore, and in curly braces we'll have treatment variable equal const marginal effect print dfnz. So now we plot the graph of worry work and worry mental. So dfnz dot kite worry work dot hist of bins equal 50 comma label equal worry work, dfnz dot kite worry mental dot hist of bins equal 50 comma label equal worry mental, plt dot legend open and close bracket plt dot show open and close bracket. Let's run that. So we see that worry mental range is the minimum and the maximum is higher than the worry work minimum and maximum. Both forms the bell-shaped curve, but worry mental is more kind of narrow. The range is smaller. We can also dig deeper into individuals by splitting the data into groups. Example with age ranges and genders. Okay, that comes to heat map. So we will continue in the next lab.